Okay, welcome to our last talk. Last but not least, we have Bruno Klingler from Humboldt University of Berlin. He will tell us about the algebraicity of the Hodge-Locker.
Well, first of all, thanks a lot for the invitation to speak here, although many people already left, but nevertheless, it's nice. Okay, so I will talk about the algebraicity of the Hodge-Locker. So what is nice is that there were many lectures introducing the objects, so I don't have to go fast and speak very fast about Hodge theory. So let me talk about Hodge loci first. Okay, so we start with the base, which is a smooth quasi-projective variety of a C. And we are interested in Hodge theory, so we consider a variation of Hodge structure. So this was introduced by Jacob. So you have a local system of finite rank over Z, and then you have an associated vector bundle endowed with decreasing filtration and a flat connection. And moreover, you have a polarization in the background. And I remind you, some of the relations is that you want that at each point this data defines your Hodge structure, where F is the Hodge filtration. And a crucial condition is Griffith's transversality. It will play a crucial role in this talk. So this is a polarized edges. And what is Griffith's transversality? Well, it tells you that if you look what the flat connection does on the filtration, then well, the filtration is certainly not preserved, but it is shifted at most by 1. So you go just in a piece which is a bit larger. And of course, you have to think that, as Jacob explained, we are motivated, of course, by the geometry. So this means that the cases we are interested in is a case where we have a smooth morphism projective. So the fibers are smooth projective algebraic varieties. Their cohomology have a Hodge structure, and the typical gadget that you get is by looking at the family of the ice cohomology of the fiber. And you get this local system of the cohomology, and this gives you your favorite variation of Hodge structure. Okay, so in this situation, so maybe for those who are not familiar with this notation, this is just the family of the cohomology of the fibers for all the points S, let's say in S1. Okay. Right. So now, what are Hodge loci? So they were also introduced by Jacob. So here I will take a small modification. Is that I will not consider only Hodge classes in such a guy. For instance, if I work in odd degrees, there are no Hodge classes. So I will take all the variations of Hodge structure generated tensorially by V. And so I will consider the Hodge locus. So this would be the set of points in the base, such that if I look at the fiber at that point, so this is a Hodge structure, and I am asking that when I look at all the possible tensor power of this Hodge structure with its dual, then it has more Hodge classes than the very general fiber. So as exceptional Hodge tensors.
Sorry for the stupid question. In general, taking dual tensor product, direct sum of all the structures.
This is a Tanaka category you like. Okay, so this is the main object of this talk. So this is what is called the Hodge locus. And Jacob stated the main result in that direction, which is the following theorem of Catani, Deligne, and Kaplan. This one is done from 95. And it tells you that this Hodge locus, which is defined pointwise, is actually a countable union. Of algebraic subvarieties. Of irreducible, let's say, algebraic subvarieties of S, and this is the one that I will call the special. This one is laying 2.
Is something also known as the Noether locus sometimes?
Sorry?
There's something called the Noether locus.
So I will come to that in a very special case. It's called Noether-Lefschetz locus, but it will be one of my examples, so I'll come to that. So those irreducible components of that set, I would call them the special subvarieties of S for V. Okay? So it's kind of nice. Each time you have S and you give yourself a variation of a Hodge structure of S, and then you get this countable collection. And as also mentioned by Jacob, this in the geometric case, so when you start with a variation of that, is predicted by the Hodge conjecture, because all these Hodge tensors should correspond to algebraic classes in some product of X with itself a certain number of times. And so, and now algebraic classes vary nicely in families because you have existence of Hilbert schemes. So this was noticed by Weil in 1979, I think. Okay, and Jacob also explains the interpretation in terms of period maps. Namely, if you have this variation of Hodge structure, equivalently you can see it as being given by an analytic object, which is a map from the identification of S to some period domain quotiented by G of Z. So I will come later to some refinement because I will need a more precise description of the G's that I use compared to what Jacob explained. And this map is called the period map. And it is holomorphic and horizontal. So this horizontality tells you that if you look at the image of the tangent bundle, then actually it is contained in what is called the horizontal tangent bundle of D mod gamma, so corresponding to a non-integrable, very small distribution. Sorry?
The marker,
I can try, but I think I will soon run out of options. Right, so there is this system of differential equations satisfied by this map, actually. All right. And then the locus can be nicely described in terms of that map. So we have this period map. And if you don't like this period map, you can think that this is essentially an immersion because of the theorem that was also mentioned by Jacob, that you have using omnimality can prove that you factorize and then you have a closed immersion. Okay. So D mod gamma. Now inside D mod gamma, you have a lot of, you have a countable collection. Let me make it like this way. You have a countable union of guys looking like D mod gamma, but for smaller groups. And this is countable because all the groups in the picture are defined of a Q. So D prime mod gamma prime. And then the Hodge locus is just the preimage and the phi of this countable union. So we have this diagram in terms of the period map. And then Jacob also explained that with Ben, so Jacob, Ben, and I, we proved that this map is definable in Rnx. And so with D prime mod gamma prime being definable, and so you recover the Catalan-Kaplan theorem using Peter-Zell-Starchenko omnimal char, right? Because you take the preimage of this definable guy and the phi's, this is then definable here, and this is also complex analytic, so it has to be algebraic. So this is nice, we have this very nice theorem, but what I want to emphasize is that although we have this theorem, really understanding that locus is complicated. And the reason is the following, I think I should emphasize that, okay, usually people say that the Hodge conjecture is about taking Hodge class and proving that you can realize it as the class of an algebraic cycle. But actually, if you give me an algebraic variety, good luck for picking a Hodge class. What does it mean exactly? I mean, usually it's already difficult to put your hand. So I would rather say that you have two sets that you don't know, and you want to prove that one is subjective. The natural map is subjective. And so for Hodge loci, it's exactly the same thing. Even if you have this nice collection, if you give me such a family, usually I'm completely unable to describe explicitly that guy. So the goal of the talk is basically to describe some property of this hot locus. So, but before doing that, because we didn't have time during the tutorial given by Jacob, I think it's nice to have more examples. So let me do that. So Jacob described in detail the simplest example. Let me nevertheless repeat it. So this is the case of a family of elliptic curves. So let's take the universal elliptic curve. So the moduli space is y0 of 1, and this is the universal elliptic curve. Okay, I should put some other structure, but forget about that. And then in that situation, what is the PN map? Well, the identification of y0 of 1 is nothing else than as a complex line. And then you have this complex line, which is mapped to d mod gamma. In that case, d is just the Poincaré path space, and gamma is just SL2Z. And okay, so what are you doing? You are taking an elliptic curve here, and you are mapping it to the H10 of E seen as a line inside a two-dimensional locally constant vector space. Okay, so this is really what you are doing. And so this is just a point in a projective space, and it happens that actually because of the polarization condition, you arrive in the Poincaré path space inside the projective space. And so you get exactly the tau, because essentially this is completely described. Come back to periods. So your elliptic curve up to multiplication has only one non-trivial holomorphic one form, and you have fixed a basis for the homology in your topological surface. So it just takes a ratio of those two things. So this will give you a number, and this number will lie in H, and you take the class modulo SL2Z of Z. Okay? This is a parameter tau. And what happens, of course, in that case, that everything is very simple, in the sense that this map is actually the biomorphism, and you are just mapping here to the tau. And tau is C modulo Z. Right. And so the inverse map here is really what is called the J function. So this is the classical picture. Now, what about the Hodge locus in that situation? Well, this is very simple. You are looking where you have exceptional Hodge tensors in this situation. So the variation is the variation of the H1. Of course, H1 is weight 1, so there are no Hodge places there. So the simplest even dimensional thing you can construct are just the endomorphism. So let's do that. And so you want to compute the endomorphism as Hodge structures of H1 of an elliptic curve. Then you know the answer. You get either generically this is Z, you have nothing, or you get an order in Q of tau if tau is imaginary quadratic. And so your diagram is nothing else than y0 of 1n, which is identified with H modulo SL2Z. And here you have the union of all tau imaginary quadratic of well, those points, the class of tau, this collection of points in this quotient. And here you get the Hodge locus of your family, which is the union of the J of tau. Okay. This diagram in this very peculiar situation of the same tau imaginary quadratic. So what do you see on that example? Well, you have a lot of such guys, namely actually one interesting thing, basic result in transcendence of the J function tells you that those guys are actually algebraic numbers. So you lie in Q bar, and you are dense for the usual topology. Okay, so this was the example summary of what Jacob explained. I think it was useful to start with this example. So let's move to the next case. So the next case is a family of abelian varieties, which is also kind of very classical. So this time you replace your universal elliptic curve by the universal abelian variety of G. And then I don't want to give the precise description, although you can do that in that case. So again, you are parameterizing weight 1 Hodge-Rafson. It means cohomogene degree 1 of your abelian variety. So I just want to emphasize that you have two kinds of very different objects. Well, you have the same kind of guys here, where you have to have a lot of endomorphism, and this corresponds to the CM points. Right? I mean, those points I should have emphasized, those J of tau, these are exactly the CM elliptic curve. Complex multiplication. So those guys will exist here too, but you will have other things. For instance, you will have what I denoted by AGK. So you can look at other kind of Hodge classes appearing, namely, for instance, when A at the point S, so this is a set of point S in AG, such that the abelian variety at that point is isogenous to a product. Where AK is of dimension K, and K is between 1 and G minus 1. Okay? So this will give you a countable union of positive dimensional algebraic varieties inside those guys. And again, you have that this locus is defined over Q bar. I mean, each of the, in the sense that each irreducible component of that thing is defined over Q bar, and it is dense in AG. All right, so let's try to move to something maybe more sophisticated, in the sense that we are not interested in degree 1 cohomology, but in a higher degree. Those examples are very special because, as Jacob explained, we know that in this case, Griffith's transversality is trivial. But let's move to outside this case. So I will do as Johan. I will take the simplest things you can think about, namely hypersurfaces in the projective space. So let's consider X and D, the universal family of smooth. So this is an open set. So I parameterize all hypersurfaces in Pn plus 1 C of degree D. So this is parameterized by this big projective space. And now I consider only the smooth ones. So this is an open condition. So UND is an open subspace there. And I take the universal smooth hypersurface of degree D in Pn plus 1. Right, so n is the dimension of my hypersurface, D is its degree. And we are thinking secretly that we're interested in the variation of the only interesting cohomology, which is in middle degree. So we look at Rn F lower star Z on X and D. Okay, so this is the family of the middle cohomology of my hypersurface. Good. So let's take the simplest example, the case n is equal to 2. And I come to the Lefschetz locus. So, so in that case, this means that I'm looking at surfaces in P3. And we are interested in the degree 2 cohomology. Okay, so there is a classical result of Noether that tells you that as soon as D is larger than 3, then generically there are no interesting Hodge classes, in the sense that general such hypersurface XS satisfies that its Picard number is 1. In other words, any curve inside XS is obtained as a complete intersection of XS with a hyperplane in the projective space. Okay? This is what it means. And so this means that if I look at the Hodge locus for this family, U2D, for this morphism F, then it contains the Noether-Lefschetz locus, which is by definition the set of points in U2D such that this Picard number is higher than expected. So Picard number of XS is strictly larger than. So rho of XS is the rank of the Picard, traditional notation. And then there are some classical results about that. So what are the classical results? Well, this is called the Noether-Lefschetz locus because Noether and Lefschetz proved before Catani, Deligne-Kaplan that if you restrict to this locus, this is a countable union. Is a countable union of algebraic varieties that we know now in general. But what is interesting is that people studied the density, and it was proven that the Noether-Lefschetz locus is dense, actually, Zariski dense. And then it was improved by Green, who proved again that actually this Noether-Lefschetz locus is dense for the analytic topology. Okay, so a picture very similar to what happens in weight 1, except here we are in weight 2. And so in particular, because this is true for the Noether-Lefschetz locus, this has to be true also for the Hodge locus. Okay, so let's try to move in a higher dimension. And here, basically, nothing was known before Catani-Deligne-Kaplan result. So if you want to describe explicitly what is this Noether-Lefschetz locus, or more generally this Hodge locus for the universal family of hypersurfaces of the grid D in Pn plus 1, then, well, basically nothing was known. So the goal of the talk is to try to get at least a partial answer. So let me state as a motivation an example of what we prove. So theorem, which is due to Baldi and myself and a little more. So take this family. Then if n is at least 3, and if the degree is at least 5, and we have to get to remove the bad case of quintics, in P5, then this Hodge locus. Okay, so we can now describe the full Hodge locus, but we keep only the components of. So we know this is a countable union of algebraic varieties, and I keep only the components which are positive dimensional when I look at them in the period domain. So their image under the PL map is positive dimensional. I'm not the pre-image of a point, but PL map. So I will denote this by pos for positive dimensional, and the claim is that. So let me write this. This is a union of special subvarieties of positive period dimension.
You said, sorry.
Yes.
In general, the map is immersion, no?
Yeah. So if actually in this case this is not an immersion because you really have to, for instance, take the quotient by the linear group acting on that space. But this means that once you suppose this is an immersion, this is really the dimension of that locus. Okay. So the union of the special subvarieties positive period dimension is algebraic. So this is not a countable union. It is algebraic on the nose, which means that there are only finitely many components of maximal dimension. And you see that this is completely different of what happens for AG, or in this case, in dimension. One remark, and this will be a general remark in all the talk, is that we know nothing about the zero-dimensional locus. Okay, so what I want to explain is a kind of heuristic that, and the general theorem in the background of that special example. But it tells you that, and I think this was really not expected by people in Hodge theory. All right, so questions about this statement?
Why is 4, 5 excluded?
It will come. I will explain when it comes to that.
Do you know what was expected? Because
Sorry?
this was not expected. What was
No, I mean, people knew by Cataneda and Kaplan that you have countably many special subvarieties, and actually you really have countably many. It's just that the number of maximal ones is finite.
So it was
So
expected.
you have a lot of them, but they are all contained in finitely many maximal ones.
It was expected that there'd be an infinite family. Right?
Yeah, and that this would be a true countable union without any relation between them. Right, so the general goal of the talk is to try to go beyond a little bit Cataneda and Kaplan and trying to understand better the distribution of this Hodge locus. And so let me come back to the picture we had, and we try to understand Hodge loci as an intersection problem. Right? And this we already know because we have the period map. But I will need to refine a little bit the image of the period map to make things more precise. So if you start with, let's say, a polarizable Hodge structure, and actually I can associate to that a group, which is the Mumford group of that Hodge structure, which is, let me give the definition, it's just a fixator. This is the guy that really describes completely the Hodge structure for you. This is a fixator of all Hodge tensors, so fixator in GLB, Q of all Hodge tensors for V. So not only the Hodge classes in V, but the whole Hodge classes in all the possible tensor power of V and its dual.
Tanaka and Dul.
Yes, this is the Tanaka group of this category, the subcategory of Hodge structure generated by V, tensor V generated by V. So this is a reductive Q group. And reductivity comes from the hypothesis of existence of polarization. Okay. So now if you start from not a single Hodge structure, but from a variation, so a polarizable ZVS, then you get this group for any point in the base. You get this group GS, which has to be locally constant because on a big space, which is a complement of the Hodge locus, because on that part, you know exactly that there are no exceptional Hodge tensors. So this is this correction, you get this GS, and you get a locally constant group outside the Hodge locus. And so actually what the period map parameterizes is rather those Mumford groups of the fiber than just really the Hodge filtration on one given V. So this means that actually you can refine, this is exactly the same picture. You have the period map phi to D mod gamma, but now D is actually homogeneous under the real points of the generic Mumford group. So D is what is called the Mumford domain, but you can forget it. You just call it a Pierre domain for G, which is the generic Mumford group. G of R, where G is the generic Mumford group of the variation. And gamma, as usual, is G of Z in my case. So now suppose you have a special subvariety, Y. inside Sn. This means that when I restrict my variation of Hodge structure on Y, there are more exceptional Hodge tensors. So this means that the joint Mumford-Tate group on that Y becomes smaller. So it becomes smaller, so I get some Gy, which is a joint Mumford-Tate group, and associated to this Gy, I get a new Mumford-Tate domain, which is an orbit of that group inside D. And so this gives me this embedding here. And Y is actually the preimage on the phi. Well, it's an irreducible analytic component under the preimage of that guy. Okay? So I shouldn't put this. This is really so Y is phi minus 1 of dy modulo gamma Y. And take some irreducible component there. Which means that to understand that guy is the same thing as understanding an intersection. You want to understand the intersection of the image of S and the phi and dy with gamma Y. In d mod gamma. So really Hodge loci are about taking intersections. And as we have learned during this week, an intersection is either typical or atypical. So let me specialize the definition of atypical in this situation. I will say that Y special inside S for V, special for V, is atypical, well, if it is not of the expected dimension, namely if, well, the codimension, let me write it this way, the codimension in phi of S of phi of Y is smaller than the codimension in d mod gamma of dy mod gamma Y. Right? This is the condition that phi of Y is of larger dimensions than expected. And otherwise, I would say that it is typical. And so out of this, you get the natural decomposition of your Hodge locus as the union of the atypical one, union the typical one. Okay? Just tautologies up to now. Now, the idea is that things which are atypical are rare. And so, this is the Zilberpin conjecture in that setting. So the general heuristic of this kind of problem is the following. The conjecture, Zilberpin. So the Zilberpin conjecture was done for Abelian varieties and for Shimura variety, for mixed Shimura variety, and then for ZVHS. I made this conjecture in 2016, I think, and actually now with Baldi and Ulmo, we have I will give the stronger version. At the time, I was adding some stupid technical condition, which actually is not needed. And the conjecture is that the Hodge locus, which is atypical, should be always algebraic. Right? They are rare, so they should be algebraic. And I remind you, it does not mean that there are only finitely many special varieties which are atypical. It means that there are only finitely many maximal ones. There exist only finitely many atypical special varieties maximum for those properties. So now I think I'm seriously in trouble. Let's see. Let's try this one. Okay. So is the conjecture clear? So inside this Hodge locus, I'm just picking out the atypical ones. So I'm saying well, their union should be an algebraic variety. All right. So let me move now to the results. So for stating the results, I will make an assumption in order to simplify the statements. So I will assume that the group, the joint Forte group of my variation is a joint, and also equal to the algebraic monodromy group. So you have a local system, it has a monodromy, you take the Zariski closure of that thing. This is a semi-simple group. Actually, Deligne tells you that this semi-simple group is always normal inside G. So essentially, you are in a product situation, and what I'm saying is that I'm killing the second factor. So it's algebraic group. Actually, this is not. This assumption is not a big problem. I can always reduce to that case. The true important assumption that I'm making here, I'm assuming that G is Q simple. Right? There could be many factors. But for the statement, it will be much easier to have a Q-simple group. Then in that situation, there was a first result that I proved with Obninovsky 2 years ago, saying that maybe this conjecture has a chance to be true. It was theorem 0. And it was saying the following, that if you take the Hodge locus, so I keep only the positive dimensional component, positive period dimension. This is either algebraic or it is Zariski dense. In other words, this countable union of algebraic varieties, you can ask, what is this Zariski closure? This is the first question you want to ask. And you could expect that you get, in some sense, any kind of algebraic subvarieties of S. And what we prove is that it's not true. Either it is algebraic, or it is Zariski dense. Zariski closure is everything.
Sorry?
Yeah.
And in the conjecture, this positivity condition appears? Or?
No, in the conjecture, and this is important, this is really for the full locus. But of course, for the results, we'll get results for the positive one. Okay, so it was in 2020. Okay, so now let me state the recent results with Baldi and Ulmo. So theorem 1. It says the following, that if you look at the Hodge locus of S, so now I take the atypical locus, this is the one I'm interested for this conjecture, and now I take only the positive period dimensions components. And then we get the result. Is algebraic. Always. So this is the first result. So if you want, this is the geometric version of Zilberpink. What we don't have is what happened for the points. We could have a lot of atypical points that we cannot exclude yet. Okay, so this was theorem 1. Theorem 2, also with Baldi and Ulmo, tells you the following, is that if you look at the typical locus, then this typical locus is either empty or it is analytically dense. If it is not empty, it is automatically analytically dense. Okay. Okay, so completely different directions, but this is what is expected by this kind of conjectures. Typical and atypical have nothing to do together. Now, what would be nice would be to have a criterion to decide in which case you are, and this is essentially what was missing here, right? You see, I mean, in some sense, this 1 and 2, they really refine this. And so the theorem 3 is a criterion. It tells you, also with Baldi and Ulmo, it tells you that if the level of your variation of a structure is at least 3, so I will explain in a few seconds what is the level, if I can. If the level is at least 3, then the Hodge locus, the typical Hodge locus, is empty. Okay. So if you put this together, this tells you if the level is at least 3, the typical Hodge locus is empty. So this means that the entire Hodge locus is atypical, and so this tells you that the positive Hodge locus is algebraic. Hence, the Hodge locus of positive P of dimension is algebraic. So these are the results. So to explain the result, I think everything is clear except the definition of the level. So I have to define what the level is. So what is the level? Well, in fact, implicitly, Jacob described it when he described Griffith's transversality. So to define this level, take a point in S, which is Hodge generic, meaning that the Mumford group at that point is the joint one. Okay? So now this means that you look at the Mumford group, which is essentially the generic one, and so you can look at the Lie algebra of that thing. Let me denote it by G underline at the point S, and then this Lie algebra is a representation by the adjoint representation of the Mumford group, so it has a canonical Hodge structure. So this means that when I complexify this Lie algebra, which is a Q Lie algebra, then I get a Hodge decomposition, and because this is inside endomorphism, it has weight 0, so everything is centered at the 0, 0 type. So this is a Dirac sum for I is equal minus L to L of GI minus I. Okay, so this is the Hodge decomposition for that Hodge structure. And of course, I go up to the term L where GL minus L is non-zero. And so L is the level. So this guy L will be the level of my variation. So if you want, as a remark, you can interpret it also geometrically. This means that if you look at the tangent space to the Piet domain at that point, so Jacob explained to you that there is a canonical filtration on that tangent space coming from the Hodge filtration, and actually what you keep in this decomposition, this is the sum of the pieces of the form Gi minus I. I should put minus I plus I, and I is at least 1. So this is G minus 1, 1 to N. So you see that this is also the length of this filtration of the holomorphic tangent space at that point. Okay. So some comments are that the level of V, so the level of V is 1, corresponds exactly to the case where D mod gamma is a Shimura variety. And so in the examples, example 0 was that case, example 1 was also that case. Second remark is that if you want, we use this invariant because this is more intrinsic than the weight of V. So the level of V is always smaller or equal to the weight. So if you take a random variation of a structure, it will be the same. But suppose you start, for instance, with a variation of weight 1, like a family of cohomology of in degree 1. Okay? Then with that, you can take any factorial construction like symmetric power of degree n of that thing. So if you take sim n of something of weight 1, it will automatically, by weight factoriality, be of weight n. But nevertheless, broadly speaking, it's still of weight 1. And this is exactly what this level will see. The level will be 1, while the weight will be n. So this is the correct invariant, not the weight.
Is the Hodge filtration of the algebraic compatible with the Lie bracket?
Yes. This is, yeah. This is what I call a Lie-Hodge algebra. So the Hodge structure is really compatible with the Lie bracket. Okay, so these are the invariant, and so now what I'm telling you here is that essentially if you take a generic variation of a structure, so the level will be at least 3, and so if you get out of families of abelian varieties, which are level 1, and out of level 2, which is still a little bit mysterious case, where things depend on the actual Manforte group that you get, in level at least 3, and under the assumption, which are here, I did not write them, but they are valid in all the theorems. Otherwise, the statements are more complicated. You get this. Okay. Other questions on the statement? So if you see this, then what can happen? Well, you understand that in level 1 and 2, these are the only case where this thing actually applied, namely where the typical large locus is not empty. This is necessarily level 1 or 2 by the third theorem. And so in that case, you can be analytically dense. So in some sense, we are completely solving the alternative here. Another remark is that, okay, so now there was a theorem on the hypersurfaces. So the matter is to compute the level of the variation. And so the cases that we had to exclude is just because the level was dropping to 2. Okay. And in all the other cases, it was at least 3. So you see that for hypersurfaces, this is really general. As soon as the dimension and level are high enough. Okay, so we have 10 minutes. So what I want to do now is to relate this to the other aspects of this week. So try to give you some idea how we can prove this kind of thing. So maybe I will, can I just shift this? The definition of the level is clear for everybody? Yeah? So you move this here, I will try to keep it, and then, yeah, to come back to this conjecture, you see that the main open question now is really what happens for points. I think everybody's excited about that, but nobody knows how to touch this. Just a remark for the non-expert is that in the case of Shimura variety, you have a lot of information about the special points. These are the CM points. You know that they are defined over Q bar. You know that you can study the Galois orbits. Okay, this is far from easy for sure, but at least you have something. If you start from a variation of a structure that comes from geometry, which is defined over Q bar, we don't even know that the special points are defined over Q bar. And even if we knew that, it would not be clear what is the Galois action there. So there is very little hope to be able to say anything using Galois orbits. Maybe there is, but at least for me, I don't see how.
That's the zero-dimensional components.
Yeah, the zero-dimensional components. This is what I call the special points.
Well, those come from the intersections.
So they are more complicated because they are not necessarily CM points, right? They can come just by intersection with something really positive dimensional with that thing, and which are really atypical, nevertheless. And
but even the worst CM points.
But even the CM points, I don't know. Okay. Yeah, so the simplest example, I think, to give you is you take the classical one-dimensional family of Calabi-Yau three-folds, which are the mirror quintic. So it's a very simple family on P1 minus 3 points. And the question is, are there finitely many CM points or infinitely many? And nobody knows. Okay, so of course, I don't think this is the place to explain in detail, but I just want to relate this to what we, ideas of proof. So theorem 1 here about this algebraicity. So this is a finiteness statement. And so actually this is now pretty standard. It's not particularly deep. It's just that you have to realize that it works. So this is an application of ActionUL for the VHS. So proven by Ben and Jacob. So Ben explained a more general statement. He asked me to mention the guys, so let me mention them. So nowadays, the point is that in their proof, they really use, I want to emphasize this because this was also on ominimality. So their proof uses a lot of ominimality, but there is a new proof, as Ben explained, which is in some sense simpler, does not use at all omnimality. So let me mention, because I think Ben forget to mention them. So I'm bad with accents, but I think this is this. So Blasquez-Sans, Casal, Freitag, and Naglu. There is no omnimality at all. And I want to emphasize that I think the proof is really much easier. No doubt about that. Okay, so I think this is worth, philosophically speaking, I think it's worth really mentioning that now all this part is entirely inside algebraic geometry. Okay, so how do you deduce from ActionUL this kind of finiteness statement? Well, if you use a bit of omnimality, it's always the same game. To prove that something is finite using omnimality, you prove it is definable and countable. And this is exactly what we do. Okay, so we parameterize. One parameterizes a set of maximal atypical components of the hard locus of positive period dimension by a set which on the one hand will be more or less clearly definable, and then what you do is that you really use the full power of ActionUL to say that it is countable. And so doing those two things together, you see that this is actually a finite set. This is basically really how you use omnimality. Okay, so maybe I should recall, because Ben gave a very, very general statement, and I don't think Jacob had time to repeat the precise statement. So really the theorem due to Ben and Jacob, so Zimmerman tells you that if you have something algebraic in S across D, or let's say D check, the compact dual, which is an algebraic variety, and suppose you take an irreducible component of this with the graph of the period map, meaning that you take W intersected with this guy of a D mod gamma, and you take, so now this is analytic. You take an analytic irreducible component, so maybe I'll just put 0 here. And then it tells you that if this is an atypical intersection, if the codimension of this U in S cross D check is strictly smaller than the codimension of W plus the codimension in S cross D of S cross D of a D mod gamma, then there is a good reason for that, namely the projection of U on the first factor, so in S, is contained in a strict, well, not special, but weakly special subvariety of S. So this is the statement that we use, iterating to get this countability statement. Okay, so that's for theorem 1. I don't want to say more here. So what is maybe the more general, although very easy piece is it's just a matter of realizing that it has to be true, is this. And this is very easy. This is purely algebra theory. So I want to keep this. Can I erase here? Yeah. So, and here, the key word is, of course, Griffith's transversality. So, for theorem 3, this is just basically theory plus Griffith's transversality. So why is that? Well, you prove the following elementary proposition still under the assumption that the group is a joint equal to the monodromy. So let's write GC, the Lie algebra at a generic point of my generic non-Forte group. So this is direct sum for I is equal to minus L to L, GI minus I, where L is the level. Then there are two statements. One which is independent of the level, which is a general property of monodromy group that tells you that this Lie algebra is generated by G minus 1. It's generated in level 1. That means that if you have another Lie Hodge subalgebra contained in G, such that G prime minus 1, 1 is equal to G minus 1, 1, then actually G is equal to G prime. Okay? All right, so, and now the only key statement, I'm ashamed that it took me such a long time to see it, but that's life, is that if the level is at least 3, and G prime is a Lie Hodge subalgebra of G.
So one is a general thing about the Lie algebra.
Not about the algebra, you could have gaps, but what I'm saying is you could have gaps in the Lie Hodge structure, things appearing in higher degrees which are not generated in degree 1. But what I'm saying is that under my assumption that G is equal to the monodromy group, for monodromy group it does not occur. So this is really like this. And so suppose that your level is at least 3 and that G prime inside G is a Lie Hodge subalgebra with the properties that all the pieces in degree is 2 have to be contained in G prime C, then G prime is equal to G. So now, if you believe in this exercise in Lie theory, and the reason is that, okay, if you have this means also that you have G2 minus 2, because everything is defined over Q, so you have a complex conjugate. Now you use the fact that the level is at least 3, so you can take the bracket of G3 minus 3 with G minus 2, 2, and then you will get in G1 minus 1 or G minus 1, 1, depending on what you want, and then you can apply this. You just have to prove that you generate the full thing, but this is easy. And this is what you can't do if you are in level 2, because you touch only a very small piece of G0. All right? Let me take maybe 2 more minutes. So suppose now that Y inside S is special, and suppose now that Y is typical. If Y is typical, what is the condition? If Y is typical, this means that if you look at the tangent space of the image of S plus the tangent space with the Piet domain defining Y, this has to be the full space. Right? You want a typical intersection, so you have to get the full D mod gamma. But now recall Griffith's transversality. This piece has to be contained in G minus 1, 1. Okay? And this guy, we know that this is a direct sum for all I larger than 1 of the Lie algebra GY minus II. Okay? And this has to be equal to the full sum of the GY minus the G minus II, I larger than 1. Okay? We have that this, well, at least this plus this has to be equal to this, but in particular this plus this has to be equal to this. So this means that all the pieces in degree at least 2 have to appear here. And so you can apply this lemma and you are done. Okay? That's what Griffith's transversality tells you. Okay, so for theorem 2, basically there was an old argument of Chai applying in Shimura varieties. And you can run the same argument as soon as you have one typical intersection, and this gives you the usual density. So maybe I want to finish, I wanted to say a bit more, but let me just summarize in 2 words. So now suppose for arithmetic geometries that you start on a situation where your variation of Hodge structure is defined over a variety which is itself defined over a number field, not over C. Then the Hodge conjecture will predict that this Hodge locus is defined, is not only a countable union of algebraic varieties, but that those special subvarieties have also to be defined over Q bar, right? Because the same Hilbert scheme argument runs, but now over Q bar. And what we prove under the same assumptions is that at least if you take the maximal components of the positive dimensional Hodge locus, then they are actually defined over Q bar. This is a result of myself with Anja Dynowska and David Urbanik, a student of an ex-student of Jacob. And in particular, this tells you that when you are in the situation of that theorem, then this positive Hodge locus is algebraic and defined over Q bar in that situation. Okay, so I think this is kind of nice. And as I said, the main obstruction is that for points we don't know. And we don't know for good reasons, because this is seriously related to conjectures that Hodge classes are absolute Hodge. Okay, so I think I'm done with time. I stop here.
Any questions?
Actually, this argument is quite true. Why is the intersection transverse if it's typical?
Sorry?
And so you said that the sum of the tangent spaces.
You see that you want to have this, but you know that this species is entirely contained in the G minus 1, 1
No,
here.
I mean the part at the beginning. So typical intersection just means that the dimension of the
But I'm taking the
space-
intersection in the full space, so I
the
have
full
to,
space, including
so
the tangent.
I have to generate everything.
Other questions?
I'm just curious, this number field that you get things defined over, is
Yes.
it just the field over which the Hodge structure and the base is defined, or do you need something else?
So this is kind of surprising result, is that actually it's enough that the base is defined over a number field
Okay.
for getting for this Hodge locus. If I would like to look at the locus of Hodge classes in the full bundle of it, then I would really need that the Ram incarnation of the variation is defined over the same number field. And then, well, you know, I mean, this is always same business. You will get finite extensions, but you don't know which one.
Other questions? Okay, let's thank Bruno again.